In this later part of this lecture, I'd like to introduce some transient response of closed controlled buck converter. So this is buck converter. You have been using this power stage all the time, and this is 3-pole 2-0 compensation we just went through. So we are using this. Again, this is the best structure. Other than this, will provide the world's characteristics, transient characteristics. Any combination of this, other than this, is worse than this one. So they found out this is the max, the optimal structure, and we'll discuss that later. Okay, and then you clearly understand why this one is the maximum, the optimum structure, and you will know how to determine these values. Compared to this power stage component, this operational amplifier, and this is nothing. Okay, this cost of this is very, very small, maybe $1, something like that, less than that, very cheap. But it determines, it governs the dynamic characteristics of this and the stability of this buck converter. So having the capacity to design this is very important. Okay, and this is the optimal value. I designed this, so this is gonna be optimum structure and values. And operational condition, output voltage is 4 volts because we have this reference voltage, and this has 2 capacitors and 1 resistor. So it satisfies the requirement of the DC regulation. So in the steady state, our voltage is always 4 volts. And the switching period of this is the same as this. So this is switching period. So it's the operational frequency is 50 kHz. We use the 2-pole, 3-pole 2-0 circuit for the voltage feedback compensation. And in transient response, we will be changing this. The value of resistance will be increased and decreased, and it will be decreased beyond the level of R critical, which place the converter on the boundary of DCM and the CCM. So in some transient response, this converter will go to the DCM mode. Still, this output voltage is regulated at this value regardless of operational mode of this. Because we have this structure which satisfies the requirement for the DC regulation, and the input voltage will be varied, and we will be observing this inductor current and our voltage and control voltage. Okay. This output of this voltage feedback circuit, output of voltage feedback compensation is control V-con, and this is the lamp signal generated inside of this, maybe probably in the PWM IC chip. Okay, so, and we will be watching this. This is switch drive signal. And before observing the transient behavior of this, we need to do some steady state analysis in CCM. Assume converter is CCM, and R is 1 ohm, and the input voltage is 16, and this is below the R critical. So converter, R critical is 5 point something, 5.88, something like that. Oh yeah, this one, 5.33, okay? So it's way below this one, so we are in CCM. So our voltage is regulated at 4 volts, so duty ratio must be this. This is first, okay? So by the feedback mechanism, this should be this one, and IR is this one. Then fluctuation of inductor current is based on this on-time slope and the on-time period, 1.m, and R critical. This is the formula for the R critical. Assuming this LTSD is fixed, that value is 5.33 ohm. All right. And somehow we want to know the steady state value of this control voltage. This is the simple way, the geometrical construction to evaluate this steady state control voltage. So this is VRAM. VRAM start from here and go to this one. So height of ramp is VM. This the bottom value can be 0, or it can be biased at some value. Okay. So absolute value of this bottom value is not important. This variation is important. So maximum variation is this one, and at this value, this switch is turned on, turned off at this moment. Okay, this is TS and the DTS. So you know this triangle and this larger triangle, they are in the same shape or whatever. So it has this kind of relationship, ratio between this and this, the same as the ratio between and this. From this simple geometry, you have two triangles, small one, larger one, and from this you have evaluate this. Okay, so control voltage is this one, 0.95. Right. So we already know this, and you have the P-sim schematic for the step load response. So this is a 3-pole 2-0 compensation, and this is reference voltage, and this generate the ramp signal, and ramp signal is this one, 3.8. Is actually this is the height of this one. Assume this is 0 for convenience, then this is 3.8. Okay, this one is 1, then it becomes 4.8. Okay, so this is the 3-pole 2-0 compensation circuit. 2-0 circuit. This is a PWM block, and this is what? This is 20 microsec, and this pulse train is period is the same one, right? So this, with this you can watch this inductor current. Okay. The P-sim has bunch of this scope, oscilloscope type something. Then this is for the current measurement, and this is voltage measurement. Maybe you don't need this. You can directly connect to this, or if this some voltage is floated, if you want to measure voltage between this and this, then you need to use this. This is a floating voltage oscilloscope, and this. But here you can remove this. It really doesn't matter because it has everything has the same ground here. All right. This is the waveform of this, and this part is the step load transition, and this drive signal is functioning in complementary manner. So for the half the cycle, this is turned on, this is turned off, and the remaining half cycle, this is turned on, this is turned off. So you are switching 1 ohm and 0.5 ohm. So R is 1 ohm and 0.5 ohm. Okay, they are alternating. Okay, and this is a transient response. I simulate using this. And this is the initial inductor current is way high. Okay, this is a transient period. There is no soft start scheme. Soft start scheme. This is very dangerous, and it will kills. It kills your switches, diode. So during this on-time period, people they increase duty ratio gradually. So actual input, the inductor current at input stage. The startup stage is something like this. This is called soft start. Soft start. With soft start scheme, this will be smooth. It don't go like this. Then this is what? This IR current is load current, and this is 1 ohm. No, this is 4 amp, 8 amp, something like that. So this is 4 amp. 5 amp, 8 amp, 8 amp, 4 amp, okay? During this period of time, there is a small overshoot and undershoot. This is our voltage, okay? So division is 5 volt, so this is the initial overshoot, can be eliminated, the soft start scheme, something similar to this. And during this part, if you magnify this, if you take a close look at this, there is some undershoot. This voltage is 4 volt and goes down a little bit, and it goes up a little bit. So this is undershoot. This is overshoot. Okay. This is the overall transient behavior, startup response with the soft start, without soft start, and some load, step load change response. All right. So This is the detailed version of that. In here, R is fixed at this value, but this input voltage is stepped down from 16 to 8 at this moment, and it go back to the 16 at this moment. Right? So before this, we analyze this. This is the output voltage is about 4 volt with some ripple, and this inductor current is 4 amp with some ripple. Okay, and this is control voltage is we calculate this. This was what? This was 2 point something. No, 0.95, very similar to that. And this is a steady state Dewey ratio, okay, which is 1/4, all right, because this output is 4 and the input voltage is this one, all right. And all of a sudden, this input voltage is reduced to half, all right. What will happen is at that moment, this inductor, output voltage go down and it gradually recovers to the desired value in the steady state, right? And the inductor current is basically same as this, okay? Because there is some energy deficit, transitional energy deficit, right? So it goes down a little bit, and then this average current average value of inductor current is load current. So our voltage is going down, and load current is going down too, something like this, right? And this Dewey ratio is increasing, and Dewey ratio, this control voltage is increasing like this, and stays this higher value and come back to the original value. And the Dewey ratio, if you take a look at close look at this, Dewey ratio is increased, and the control voltage is increased also. Okay, I'll explain this in detail later, very soon. Okay, this is the waveform of the feedback PWM block. This is the control voltage and V ramp. This is switch drive signal. So initially it starts up here, this moment, and at this moment it turns on, off, turns on again, turns off again. This, if you take a look at this control voltage, it has some ripple component. So this is another constant. Maybe this is some sinusoidal waveform, something like this. And this point, this transition point is the same, because this waveform, this ripple component is periodic. Because of that, this Dewey ratio is same all the time. If you increase this control voltage, then this may be something similar to this. Then again, this instant is the same. Okay, there is just some ripple component. The ripple component itself is periodic, and then this point, as this point occurs at the same moment, so Dewey ratio remains the same. Okay, so you don't have to worry about the ripple component in the control voltage. Let me use one analogy to explain this. This is water tank, and there is some pipeline. There's a faucet. Faucet is here, okay, and the water is coming down like this. This is water level. It can be considered as output voltage. Okay. The stream, the strength of this stream is all of a sudden reduced. So this becomes weaker. This incoming stream becomes weaker. Okay? Then the water level will be going down. Temporarily, it goes down. And then this level is less than desired one. Then feedback is working. And the feedback mechanism will turn this faucet in counterclockwise direction. Okay, so more water is coming out, then this will go up. Okay, that is the same as increasing the Dewey ratio, because input voltage is reduced. So to have same level of this output, this water level, then you should increase this control voltage to increase duty ratio. Okay? It takes some time to react this because there is some time delay in between. So there is a time delay. This is relatively slow. Okay? Then you open this faucet in this direction, then this water level goes to up to the original value. This is a transitional undershoot, and we will come back to the original value level of this. Okay, so you reach to this, and you all of a sudden you increase this water stream strength. Then to maintain same level, and during the short transient period, the water level will be increased like that. Then the controller turn this faucet in clockwise direction. Okay, reduce this duty ratio by reducing this control voltage V code. This is the basic mechanism of this achieving line regulation, and this is slow, relatively slow, but this is the almost optimal response for the given parameters, power stage component. This is another one. Now, input voltage is fixed, and this is increased. Okay. Oh, let me write down this. This is undershoot, transitional undershoot due to the energy deficit in the capacitor. Okay, this is overshoot due to the energy surplus, transitional energy surplus. So it goes down. Okay, with this it goes up. With this, if you observe something opposite, something is wrong. It cannot happen that way. Okay, through the simulation and through the experiment. Okay, so the direction of this should be this way, obviously. And let me move this. Okay, this is 1 ohm. This is 2 ohm. So this is a stronger output, right? Small resistance means the larger water is coming out. Strong output. And larger resistance means weak output flow, right? So this is a steady state, and all of a sudden, the output current coming out from this converter is reduced by half. So during this period of time, the capacitor voltage is overflow. Okay, so overshoot due to energy surplus, because this is the energy stored in the capacitor, and this energy extracted from the capacitor is smaller than previous one, because this larger distance means smaller inductor current, output current, something like this. Okay, so with this we have this voltage overshoot and the voltage undershoot. This is due to the energy surplus, and this is the energy deficit. Okay, but this is fast compared to the previous one. Response of this is fast, much faster, right? There is a reason for this. We'll study this later. Okay, this is another action. This is the inevitable consequence of the compensation design. So this is fast. The previous one was slow, right? And during this period of time, there is some transient waveforms in the control voltage, but in the steady state, the level becomes the same. and the duty ratio is changed during the transitional period, but in the steady state, this control voltage and duty ratio remain the same because duty ratio should be same as long as input voltage is fixed, regardless of the amount of output current. If converter stays in CCM, remains in the same operational mode, okay, it should remain the same because not the case for the DCM. CCM voltage gain is just D fixed, all right? So that is the reason for that. This is some transient response of this converter. So I have 3 different design for the voltage feedback compensation. Later on, you will be learning phase margin of this converter. Okay, so this is some preliminary overview of what will be coming later. So you will have full knowledge to design properly. So phase margin of this case is 65 degree. This is a very good design with sufficient phase margin, and this is worst design. This is a worst design. This negative means converter is unstable. Okay, everything remains the same. You just changed this value of this, then it becomes the phase margin. You don't see the phase margin here. Later on, you will find out by some analysis. Phase margin is this one, this one, this one, and this is a transient response of for the same output changes. So this is the best design. So this is the transient response of this. This is load transient response of this, and this is a 16 degree of phase margin becomes a little bit oscillatory, and this is increased a little bit, and this is unstable one. Here this is unstable, and this is kind of stable, and this is unstable again. The difference between this mode comes from the load current. If load current changes, this is 8M period, this 8M, 4M, okay. In this period, the converter is almost unstable, but in this region, converter is very stable. Phase margin is -5 degree here, but this period, the difference is coming from this load current. This is line load condition, and this is heavy load condition. Maybe 30 degrees, something like that, I don't know. Okay, so this is kind of stable, very stable response. Okay, so this performance depends on this level of the load current. But if you have enough phase margin, it won't happen here. Okay, always remain stable. Okay, let me finish up this. This is response. Step load response. Now this is 1 ohm. So this 4 volt and 4M, average value is 4M, and this increased to this one, 8 ohm, which is much larger than critical value. Then with this, the converter will go into DCM. So DCM operation, you will see this. This is the waveform of this. This is the DCM waveforms. You don't have this. This is extra page. Okay. In original lecture slide, it was missed by my mistake. Okay. I took it out. I don't know, some reason. So, but this will be included in the post-lecture slide. All right. So this is IL is like this. So it remains 0. So it is a DCM because this 8 ohm is much larger than this R critical. Okay. Then take a look at this. This control voltage in DCM is reduced. Still output is regulated at 4 volt. But this response is very slow. Very slow. Okay, other than that, it's very similar to the previous case. And during the DCM, this control voltage is reduced than previous one, and this duty ratio is obviously duty ratio is reduced. If you compare this part and this part, you can see the reduction in the duty ratio, obviously. Okay, why is that? This is the DCM. This is a DCM gain formula, and this is a CCM gain formula. Okay, so converter is moved with this, and if converter goes to DCM with this duty ratio, our voltage will be larger than previous one. Okay, the role of this feedback controller is it should maintain this output voltage at 4 volt regardless of the change of operational mode. So controller is working and it reduces this voltage to have smaller duty ratio. This is okay. This is the proper way of regulating this. If you converter go to the DCM, while this output voltage is regulated, duty ratio gonna be reduced like this, or control voltage will be reduced like this. Okay, because of this, the difference in gain formula for the same D, this is larger than this. So smaller D in DCM to maintain the output voltage same. Right? Understand this, okay? This is the last page. This is also important. Transient response in CCM and DCM, okay? So the first one is I switched the resistance between so transition occurs in the DCM. This is a DCM and this is a DCM. Still output is regulated, but this response is very slow. This is, I changed R of 1 ohm, R of 0.5 ohm means the converter is always in DCM. Okay, response is very fast. This is relatively slow. Okay, this is very slow. This is fast. The reason for this is, okay, just 1 minute. Reason for this is, originally this is a second order system. You have L and C, second order system. So it has second order dynamics basically, which is fast. When DCM is occurred, this characteristic is very similar to the first order system. Inductor current is starting from 0 and returning to the 0. So inductor current is not changing in some sense. Okay? Because of that, this shows some transient response of first order system is very slow. So DCM is very slow, inherently slow. That is the common characteristics of all the converters operating DCM. Okay? The characteristic of this peak value, size of this overshoot, undershoot, and the period, the settling time or time constant can be predicted from the output impedance characteristic of this converter. If you measure, simulate output impedance, analyze the output impedance, it looks like this. Okay, this determines the speed, and this final value, this is final value, determines the peak, initial peak. All right? This is the optimal design. With sub-optimal design less than optimal, looks like this. That will, output impedance will be like this. Something like this. That case, this determines the speed. And this determines initial peak. For that case, this is the first one. This is the with the optimal design. Hard to draw. Something like this. Okay, let me switch the color. Confusing maybe. Okay, and with that one, it has the same initial step, but it goes further, higher, and it comes back slowly, like this. Okay, this is the steady state value remain the same, and because of this difference in output impedance characteristics, it will go through this additional peaking and additional retarded time. All right. So if you obtain this, then you try to improve this. That will optimize your design. Okay? But there is a limitation. Later on, you will see, you will learn how to achieve this and what is the limit of this. Okay? Whatever you can do, you cannot obtain response faster than this. You should know where the limit is coming, something like that. Okay, sorry for the delay. Right. Okay. We stop here. Okay, thank you.